Hello and welcome to another lecture in Introduction to Astronomy. This is lecture number 13, where we will learn about stars and how we calibrate celestial distances in what we call the cosmic distance ladder. Today we will learn how to determine a star's brightness, its luminosity, and how we can learn its distance from that as well. We'll learn how color and temperature are correlated, as well as how we can use those to determine the spectral types of stars. We will also learn how binary star systems can help us determine masses of stars, because if there's not a star interacting with something, then it's hard to tell the mass of something that's by itself. We'll also learn how the HR diagram is used to correlate luminosity and temperature, as well as what the HR diagram is. And lastly, we will learn how some unique types of stars, such as Cepheids and RR Lyras, are used to determine distances in space. Stars are incredibly common in the universe, and everything we can hope to learn about them and all of these billions and trillions of stars can be done from decoding their emitted radiation and the energies that we can see in that radiation. From that, we can determine the characteristics of the stars, like how bright it is, like the intensity of the light. We can determine what color the star is from its wavelength and the energy, as well as the temperature. We'll learn how color is related to all of those. We can also determine its size and mass, as well as its composition from its spectra. We know about spectroscopy and how we can determine composition, and so that's how we determine the composition of stars, is through their spectra. And this gives us a glimpse into the conditions of these stars, and then we can compare that to our sun, and we can learn about our sun's place amongst all of these stars. So first, we're going to talk about brightness. Brightness is one of the most important characteristics of stars. And so when we are looking at constellations, the brightest star in a constellation is designated the Alpha. So in the constellation Centaurus, for instance, Alpha Centauri is the brightest star in that constellation. So we need to talk about brightness and luminosity, because these are seemingly very similar things, but they are different, and we need to really understand their difference in astronomy. So, brightness is luminosity defined as the total amount of energy emitted at all wavelengths per second. So, if we imagined a sphere around our star, that's how much energy that sphere would be receiving. However, that's different than what we see when we are looking at a star. Because when we are looking at a star, we are only on one part of that sphere around the star. So we are only receiving a sliver. So what we see is the apparent brightness of the star. Because if you remember our inverse square law, the amount of energy uh, dissipates with distance in all directions. So what we see is the apparent brightness, or the amount of the star's energy that reaches Earth. And that's different than the luminosity of the star, which is the total amount of energy that is being emitted by the star. But this is where things get a little uh, complicated. I mean, well, it already was complicated, but we need to think about this in terms of distance, because again, with our inverse square law, we know that the amount of radiation that we receive decreases with distance. However, not all things have the same luminosity. So if a star appears dimmer, we don't know if it's further away from us or if it's less luminous. So we need to disentangle these two things to determine the distance. We can't just say, oh, that star is dimmer, so it's further away. It could be that it's closer, but it's less luminous. Now we're going to talk about the color of stars. So stars come in a large variety of colors. There are blue stars, white, yellow, orange, and even brown dwarf stars. So astronomers use color as a very important characteristic tool to determine the surface temperature of the star. So this measurement is very useful because unlike brightness, the color is independent of the distance, and it only depends on the energy and the wavelength of the radiation being emitted by that star. So here are some examples of stars, of their colors and their surface temperatures. So for instance, Spica is a blue star, and so it's very hot with a surface temperature of about 25,000 Kelvin. Our sun, for instance, is a fairly average star, and so its temperature is in the middle of the star range, and so it's about 6,000 Kelvin, which gives it a yellow color. And there's also Betelgeuse, which is a red supergiant star. It is much larger than our sun. However, its surface temperature is much cooler at 3,000 degrees Kelvin, and that gives it a red surface temperature. So surface temperatures can have a wide range, with some of the hottest stars being about 40,000 Kelvin, and the coolest ones going down as cool as 2,000 Kelvin. Our sun is what we call a yellow dwarf star, and so its peak color is slightly greenish yellow with a surface temperature of about 6,000 Kelvin, and it only appears yellow due to the nitrogen in Earth's atmosphere scattering blue wavelengths into the sky. The exact color of a star is measured through filtering those wavelengths, such as in the UBV system used by astronomers. The ultraviolet is the U there. We have the B for blue and V for the visual slash the yellow. And this indicates the relative magnitudes of the star's colors for each filter. So some stars are brighter in certain wavelengths than others, so that's what gives them their specific colors. So we've talked about spectroscopy in previous lectures, so now let's talk about how this applies to stars and how we can learn about their temperature based on their spectra, because we know we can learn about their composition from their spectra. So we know that all stars are composed primarily of hydrogen. However, in the hottest stars, that hydrogen is going to be completely ionized. And since it's completely ionized, there are no electrons around the protons to re-emit absorbed photons. So the ionized hydrogen emits no spectra. Conversely, in the coolest stars, the hydrogen is not ionized and is instead in the lowest energy state. And so only ultraviolet photons have enough energy to be absorbed and give off, uh, re emit light. And so in the coolest stars, there is also very, very little uh, spectral lines from hydrogen. This actually then leads to stars that are in the middle range of temperatures having the strongest hydrogen spectral lines because they are just in that right middle zone where they are hot enough that they are having their hydrogen absorb and re-emit photons. Not all of it's ionized, and it's hot enough that they can produce those energy levels sufficient to excite the electrons. And so stars that have surface temperatures of about 10,000 Kelvin have very visible hydrogen spectral lines, which we call the Balmer lines. So we can see in this image of two spectra of Cirrus and Canopus, and we can see that Cirrus has a much brighter, not brighter, but much more obvious spectral absorption lines, those black gaps that we see in the spectra, because its surface temperature is in that 10,000 Kelvin range. So now that we know that stars have different spectra, depending on their composition, but also their temperature, we can sort stars into groups based on their spectral lines. So there are 7 classes of spectral types, ranging from the hottest to the coldest, with O being the hottest, and then going from B, A, F, G, K, and M being the coolest. There are additionally three more letters for even cooler objects, but these aren't really stars in the sense that they are fusing hydrogen into helium, but these are L, T, and Y. But why is this all so confusing in terms of letters? Well, originally the first classification system for stars was based on their hydrogen spectra, classified from A to O based on the strength of the hydrogen lines. However, hydrogen ionizes above 10,000 Kelvin, and so we need to have a wider range to account for these stars that don't have any hydrogen spectra. So in the 1890s, the astronomer Annie Jump Cannon redistributed the hydrogen classification based system, or redistributed this hydrogen classification based on temperature in decreasing order, going from O, B, A, F, G, K, and M classes that we see today. She created the mnemonic device to remember this system. Oh, be a fine girl, kiss me. But that's kind of cringe. And so astronomers have come up with a lot of variations. And so there's also Oh brother. Astronomers frequently give kooky mnemonics. There's also Oh boy, a failing grade kills me. So pick whichever one you want. If you want to remember, uh, if you want to come up with your own, feel free because it's really what helps you remember those letters the best. O, B, A, F, G, K, M. Yeah, it is. There's quite a few different ways to remember it, but it is always very useful to come up with a way to remember them. These spectral types can then be further divided into subclasses from 0 to 9, from hottest to coldest in that spectral type. So for instance, a B0 star is the hottest B-type star, while a B9 star is the coolest B-type star. The hottest O-class stars, those with surface temperatures above 28,000 Kelvin, show primarily ionized helium spectral lines, while hydrogen lines are most apparent in A-class stars, like Cirrus, who have surface temperatures near 10,000 Kelvin. So all elements heavier than helium are generally referred to by astronomers as metals. However, they are not metals in the sense that they are conductive, but we just refer to them as metals because they are heavier than helium. And so they often appear in the F through K class stars whose temperatures are in the range from 6,000 to 3,500 Kelvin. While M-type stars are the coolest stars, and those actually have spectra that contain molecular spectral lines. So I want you guys to note that our sun is a G2 type star. And so when we look on the right at these examples of spectra, we can see that the hottest stars, those O6.5, have almost looking like a continuous spectra, and the lines that are present in those would be helium absorption lines. But then as we look down at these cooler stars, we see different spectral lines start appearing more frequently, getting more apparent, getting darker. But then as we get cooler and cooler, we see many more lines appear. And so it depends on the composition and the temperature what the spectra of the star looks like. There are also these types of stars, or more accurately, that we would call objects, that are similar to stars, which we call brown dwarfs, and they are cooler than M9 type stars. So these are the ones that have the spectral labels L, T, and Y, and these are what we call celestial objects because they cannot be classified as stars because they don't derive all of their energy from hydrogen fusion. So they never reached the masses and the internal temperatures high enough to achieve that proton-proton fusion, and so many consider these to be failed stars. These brown dwarfs are really difficult to observe because since they are so cool, they are incredibly faint. But even then, we have still found over 2,800 known brown dwarfs so far. The hottest of the dwarfs are the L0 to L9, which have temperatures between 2,400 and 1,300 Kelvin. And then there's even cooler ones, the Ts, which have a range from 1,300 to 700 Kelvin. But in 2009, astronomers discovered even cooler types of brown dwarfs called ultra-cool brown dwarfs, which have temperatures in the range from 500 to 600 Kelvin, and they're classified as Y dwarfs. While in 2015, there were some even cooler Y dwarfs found with surface temperatures of 300 Kelvin. So that's starting to get close to what we can produce in our ovens at home. Y dwarfs have masses very near the masses of the largest planets. However, they are classified as a brown dwarf since their masses exceed the threshold for deuterium fusion. That is roughly 13 times the mass of Jupiter. So Jupiter isn't quite a brown dwarf because it is not fusing deuterium inside it. When we look at the nearby stars to our sun, we can see that there are not that many, and many of them are brown dwarfs. So within our local neighborhood of roughly 21 light years around, there are 162 stars. Most of the nearby stars are very low luminosity stars, low mass, and cold. So these are the M types. While there are only three that are significantly more massive and luminous than our sun. There's one F type and two A types. Many of the stars near our sun are not capable of being seen without using some sort of telescope. Because they are very low luminosity. In fact, stars with luminosity less than 1/1000th of our sun have to be within 5 light years to be seen, and only the Alpha Centauri system is this close to our sun. Only 6 stars within the 26 light years of our sun are bright enough to be seen in our sky. So these are Sirius, Vega, Altair, Alpha Centauri A and B, Fomalhaut, and Procyon. And so often the stars which appear the brightest are not necessarily the closest. So there are some stars that are up to 50,000 times as luminous as our sun, but these are quite rare. And so for this reason, astronomers have to be really careful to assume any conclusions in visible observations because these stars are often rarer than those nearby, and so this leads to an example of bias known as the selection effect. Many stars in the universe are actually in groups. So our sun is a bit of a loner and is kind of an oddball. Many stars are in binary pairs. And so this is one way that we can measure their masses. And we can see that mass does not necessarily correlate to overall size. So the only way to really study their actual mass is by studying their gravitational interactions with another body. So binary star systems are one of the most common types, but you can also have triplets or even quartets of stars. And these are often very difficult to distinguish independently because they're very far away, and sometimes the one of the binary partners is way less luminous than the other, and so its light is greatly dwarfed by its much brighter partner. And so in these cases, we need to do spectroscopic studies of these stars to distinguish the splitting of unique spectral lines from Doppler shifts in their composite spectra, which we call spectroscopic binaries. However, some systems are what we call visual binaries in that we can actually see with our just by looking at them that they are two stars orbiting each other. And this is when their brightnesses are very similar and their temperatures and sizes are very similar. And so we can see them as distinguished as two objects. We know from Kepler's third law that we can find the sum of the masses by measuring their orbital periods. So for and the semi-major axis. So for visual binaries, the period and the semi-major axis can be directly measured from their motion. Alternatively, for spectroscopic binaries, a radial velocity curve can be analyzed to determine the radial speed of the stars from the composite spectra. This radial velocity is then used to find the period and the circumference so that we can then find the masses from Kepler's third law. Astronomers calculate that most stars have masses less than our sun, and it is very rarely that they are more massive. And so, in these rare cases, we call them giants. Nearly 90% of the known stars also obey a general mass luminosity relationship. This is that the more massive they are, the more luminous. And so this is given as generally as the luminosity is equal to the mass raised to 3.9. But there is an exceptional 10% of stars which disobey this mass luminosity relationship quite a bit, and they are unique, and so we can't use that for everything. We need to uh, always have additional methods to determine their luminosity. You can't just get it from their mass. So now we're going to talk about the sizes of stars. It is very easy to measure exactly one star's diameter, and that is the sun. Other than the sun, we have to use a variety of methods to measure their diameters. So for stars that lie along the zodiac, we can make use of the moon. So when we have stars that are along the zodiac, as the moon crosses the star's disk, we can measure the time it takes for the star's brightness to drop to zero, and this gives us an approximate measurement of the star's diameter. For binary stars that are not along the ecliptic, if they are what we call eclipsing binaries, then we can measure their diameter fairly accurately. So an eclipsing binary is when stars line up in such a way that one star passes in front of the other, blocking the light of the behind one from our perspective. And so the resulting light curve periodically obscures the larger star's light that is behind, and so the diameter of the crossing object can be measured based on this periodic time as it crosses in front of the larger star that is behind it. For stars that are not eclipsing binaries or along the ecliptic, we use what we call the Stefan-Boltzmann law. And this gives us a relative ratio of the flux with the temperature. And so for a stellar surface area, we can relate that to its luminosity by the relationship that the area times the flux is the luminosity. And so this we can use relative ratios of stars with known luminosities and diameters to find the unknowns in the relationship that we have below with the luminosity and the radii. However, this requires known luminosities and sizes to compare to. So astronomers find that most nearby stars are roughly the size of our sun, and that fainter stars are generally smaller than luminous stars. However, there are a few exceptions with giants and supergiants, such as Betelgeuse in the Orion constellation, which is a huge star in terms of its size, and it has a diameter of 10 AU. So if you put Betelgeuse in place of our sun, it would be larger than our inner solar system. It would reach out past, uh, actually past Jupiter. So now that we've got some characteristics, Let's plot these and see if there are any relationships. And this is exactly what Henry Russell and Einar Hertzsprung proposed in their detailed diagram in 1913, which is called the HR diagram now, the Hertzsprung-Russell diagram. So by plotting the surface temperature, which we refer to also as the spectral class, of nearby stars against their luminosity, we can see that many stars, as the surface temperature increases, so does the luminosity. And so this creates a band from the upper left to the lower right, which we call the main sequence. However, some stars lie above the main sequence and have low temperature but high luminosity, suggesting they are very large. And so these groups are referred to as the giants and the supergiants. In the bottom left, there are clusters of stars which are simultaneously very hot but also not very luminous, which suggests that they are very small. These are the white dwarfs. And so the original HR diagram only modeled luminous stars within 10 to 20 light years of our solar system, and so this gave it a bit of a selection effect. However, today we conjecture that 90% of all known stars are main sequence stars, while the remaining 10% are giants, supergiants, and white dwarfs. So we can see an example of this HR diagram here on the right, and we can see very clearly this main sequence stretching from the upper left to the lower right. And then we can see that there are more red giants than there are supergiants, both of which lie above the main sequence. So supergiants are incredibly rare, but they are the largest and the brightest. And then we also have the white dwarfs, and then we have the red dwarfs, which are the lowest and coolest and faintest stars. Stars spend the vast majority of their lives on the main sequence. And so we saw that the main sequence was the most populated part of the HR diagram, and that's still true even when we account for this selection effect. So this is because they spend the majority of their life fusing hydrogen into helium. And hydrogen is fused into helium very slowly in their interiors. And we can determine roughly their approximate mass based on where they fall along on the main sequence. Stars that are in the upper left are going to be more massive because they are brighter and hotter. And so we can then say that since they are hotter, they have they have a larger core temperature. And so this core temperature, due to hydrostatic equilibrium, also tells us that they have to have a larger mass. And so higher core temperatures also are correlated directly with higher surface temperatures along the HR diagram. About 10% of stars lie outside the main sequence. These are in their later phases of life, where the source of energy is no longer hydrogen fusion. But because stars spend the majority of their life on the main sequence, these periods outside the main sequence are very brief. So we see less giants, supergiants, and white dwarfs compared to main sequence stars. The HR diagram is a very useful tool, and it can also be used to infer the distance to stars. However, this must be done very carefully. After a detailed examination of surface temperatures and spectra, astronomers classified stars into spectral types, but spectral types are not enough to determine luminosity, since some stars are not along the main sequence. From atmospheric pressure measurements in spectral lines, we can determine stars can be clumped into luminosity classes based on differences in pressure due to their size and mass. The most widely used system for star classification divides stars into one of 9 categories of their luminosity. We have 0 for the hypergiants, 1A, the brightest supergiants. You can see all of these. We've got the V for the main sequence, And we've got V for me. That's 5. And then we've got 7 V11 or VII for the white dwarfs. The full spectral class or specification of a star includes its luminosity class and its spectral class. So, for example, an F3V or an F35, I guess we refer to it as V here, uh, is a F3 spectral class that is in the main sequence. So our sun is a G2V type star. So it is a G spectral class. It is slightly cooler than the hottest G type stars, so it has that too, and it is along the main sequence, so it has the V. Now we're going to really start to combine everything that we've talked about in this lecture so far, and we're going to apply this to a star on its position on the HR diagram. So once we know its full spectral classification, we can know its unique position on the HR diagram. And since the HR diagram plots luminosity versus temperature, astronomers can then independently measure the luminosity and distance from its apparent brightness. This method has been historically called spectroscopic parallax. These spectroscopic parallax methods are often mathematically intensive and relatively approximate. And it is worth noting that comparatively, astronomers best study for nearby stars using measurable parallax, spectra, and luminosity classes altogether. You don't just use one method to determine the distance, you use as many as you can to give you your best estimate. And this is what we call our first step in measuring the distances in the cosmic distance ladder. And so we will explore more of these distance measuring techniques in following lessons. So we see here on the left an example of this cosmic distance ladder. We want to first we measure the distance to the nearby planets in the sun using radar, and so that gives us our first rung in the ladder, so to speak. For things that we can't use radar to measure, that are a little bit further away, we use parallax, which is that method where we look at we use the geometry of the Earth's position around the sun and the measured shift in the angle in the sky of the star, which is that parallax, and then we can apply a Pythagorean geometry to measure that distance. But that's not going to work for all stars because that parallax could be extremely small, so small that we can't quite measure it, and then we can't really use that method. And so this is where this main sequence fitting distance measurement comes into play, which is also what we call spectroscopic parallax. And so we'll see that this doesn't work for measuring other galaxies. This is only really a way to measure things within our own galaxy. And so if we want to measure the distance to other galaxies and other galaxy clusters, we're going to need even more tools to create further rungs in our cosmic distance ladder. So measuring the luminosity for further distances gets very tricky. We can't always assume that luminosity and temperature are always correlated, nor can we use these correlations to find the distances for objects outside a certain range of our galaxy. Instead, the luminosity of a star must be independently measured. But how can astronomers independently measure luminosity and disentangle it from luminosity and distance? Astronomers have researched this problem for a very long time and have found some techniques that work for what we call special stars, which we will talk about in the later slides. And so from the luminosity and distances of these special stars, we can infer the distances to other stars by comparing these two measurements and have then equivalent luminosities, or infer the luminosities from those which can then have measurably equivalent distances. So many of these special stars that we are going to talk about are what we call variable stars. So most stars have a roughly constant luminosity, but some stars have luminosities that vary periodically over time. and these are our variable stars. Among these many variables, there are two special types of variable stars: Cepheid variables and RR Lyrae variables, both of which are referred to as pulsating variable types because they change their diameter with time because they are periodically expanding and contracting. And so this pulsating effect is due to uh, these variable stars going through brief, unstable stages in their hydrostatic equilibrium, where the outward pressure is different than the inward gravitational force that is trying to balance. And so it gets larger and smaller over time. By measuring the pulsation and the Doppler effect, where the lines in these spectra are changing from blue as the surface moves towards us and then back towards the red as it moves away from us, we can then measure that shift. And the changing overall color indicates its temperature is varying, and an average temperature then might correlate to an average luminosity, which we can then use to uh, get an overall luminosity. Cepheid variable stars are this first type of variable star that we're going to talk about, and they are named after the first type that was, or the first one that was discovered, Delta Cephei, in the constellation Cephus. Delta Cephei was discovered in 1874 by John Goodricke, with periods of apparent brightness in 4.5-day cycles. Most Cepheid variables have periods ranging from 3 to 50 days, with large luminosities ranging from 1,000 to 10,000 times the sun's luminosity. And these can vary from a few percent to 10 times during their pulsation cycle. Today, several hundred Cepheid variable stars are known in our galaxy, including Polaris, which is the North Star, which for a long time varied by about a tenth of a magnitude, which has for a long time varied by about a tenth of a magnitude every 4 days. Recent measurements show, though, that this is slowly decreasing. This Cepheid variation, this period of variability in Cepheid stars is not permanent. It lasts a very long time relative to us, so could be millions of years, but as we see with Polaris, it will eventually, it's a brief period in the star's life cycle, so it does eventually slow down. Cepheid variables, though, are really important because their period of pulsation and average luminosity is directly correlated via the period luminosity relation. And since the period of pulse is easy to measure, you can then easily find the average luminosity. The period luminosity for Cepheid variable finds that the brighter appearing Cepheids have longer periods. As a result, these Cepheid variable stars can be used as signposts to distinguish the distances of stellar objects with like luminosities, for which the parallax is too small to determine. And so this helps bridge the luminosity distance conundrum that we had for these stars. There is another type of variable star, which we call RR Lyrae stars, named for the first type, the first one that was discovered in the constellation Lyra. And these RR Lyrae are much more common than Cepheids, with about 85,000 known so far in our own galaxy. However, they are far less luminous than Cepheids, and so Cepheids are used for determining further distances. However, these RR Lyrae are good for the intermediate distances between parallax and Cepheid variables. RR Lyraes have shorter periods of pulsation, often less than a day, and they typically vary in luminosity by less than a factor of 2, making these observations more difficult. RR Lyrae also exist in clusters, which have nearly the same apparent brightness. And since star clusters are approximately the same distance, this implies that these RR Lyrae variables all have the same intrinsic luminosity too, approximately 50 times the sun's luminosity. So, by clustering an apparent brightness correlation, astronomers can determine their distances after determining their luminosity for their period luminosity relationship, just like they did with Cepheids. I actually did a project in my undergrad on measuring the distance to an RR Lyrae variable star, and I found that I got a distance measurement within 13%. So, not great, but hey, 13% isn't terrible, so I'll take that. I always have a special place in my heart for RR Lyrae stars because of that. This brings us to the end of this lecture.